Hello, ladies and gentlemen, and this is mainly for period 3's class. We didn't quite finish today. We had a visitor come in, Colleen McPhee, and that took away a little bit of our time. So let's take a look at finishing off this last example, example C. We did do example D before, and but this will give you a video and a little bit more interesting algebra here. Some interesting things happen with this one. Okay, so this is really important to notice, is that if we take a look at our normals here, the normal for the first plane is going to be 2, -1, 1. The normal for the second plane is equal to 1, 1, 1. You'll notice that these normals cannot be scalar multiples of each other, which means that these planes cannot be parallel, and if the planes are not parallel, then they must intersect at a line of intersection. Therefore, planes must not be parallel and must intersect at a line of intersection. And as we've discussed up in here, this line of intersection is going to require us to have a parametric value introduced. Okay, we're used to lines being in parametric value so that they look something like this. We're going to be looking at x being x naught plus t times a, y being y naught plus t times b, and z equals z naught plus t times c. And of course, these can go together to give you your particular point plus your direction vector in the vector notation. And another way to look at this, plus t, a, b, c. Okay, so these are all different forms of writing out the same thing. The important thing here is this parametric, this t value. This is a parametric where t can go through all the different values of r. And what that allows us to do, as you recall, is it allows us to go from any point in 3 space. Okay, so here's my point in 3 space, p naught, and it allows me to go direction vectors. So maybe my direction vector's over here somewhere. We could put it so it looks something like that. We do know that if I'm going to talk about that direction in terms of components, that it has to be here, and that we take that and we apply it here. And as we add multiples of that vector, we build this line where it's b naught plus t times the direction vector. And it's this t value that allows us to move anywhere on that line. So there's a very quick review of everything that we're looking at here. So the answer that we're after needs to have a parametric. And to do that, we're going to have to introduce that parametric into our equation, our solution. So I'm going to use another piece of paper because I can, and we will start off. Let's take a look at what we have here. So I've got 2x minus y plus z minus 1 equals 0. And I've got x plus y plus z minus 6 equals 0. We'll call this equation 1 and equation 2. Let's multiply this one by 2, let's say. So multiply this one by 2, and that'll give us 2x minus y plus z minus 1 equals 0. And the other one will be 2x plus 2y plus 2z minus 12 equals 0. We're going to do a little bit of elimination with that. The signs are the same, so we will be subtracting. 2x subtract 2x is no more x's. Minus 3y, negative z, and plus 11 equals 0, which gives us negative 3y equals negative 11 plus z, and dividing through by negative 3, we're going to get y equals 11 over 3, subtract 1/3 z. So there's an equation for z. We can call that equation 3 if we want. I'm going to zoom out a little bit so I get a little bit more room to work here. So that's my z value. I'm going to take that and I'm going to substitute it back into either 1 or 2. So sub 3 into, probably easiest up here that I'm looking at is 2. And I can put it in before I multiply it by 2. There's no problem with that. So it's going to be x plus, now instead of the y, we're going to replace the y with 11 over 3 minus 1/3 z plus z minus 6 equals 0. Now I don't know about you, but I don't like fractions working with them. I always tend to make a mistake when I do. So I'm going to multiply both sides of this equation by 3. So that's going to be 3x plus 11 minus z plus 3z minus 18 equals 0 times 3 is 0. Don't forget you are multiplying both sides by 3. Now I can use this. So now I've got 3x and I've got 2 z's and I've got -7, I think. Take that over there. And so I'm going to have 3x equals 7 minus 2z. And so x is going to equal 7 over 3 minus 2 over 3z. And that gives us a second equation, which we can call 4. Now, as we discussed in class, these are looking very much like parametric equations. The only problem is I've got y related to z, I've got x related to z, and for us to have our definition of a line in vectors, we need a parametric value that we can relate y to this parametric value. We usually use t, so y is related to t, x is related to t, and z will be related to t. So what we're going to do here is we're going to introduce this parametric value, and we're going to introduce the parametric value t, and you're going to let z equals t. And what that's going to do is it's going to give us very nice parametric equations. We're going to get x equals 7 over 3 minus 2 over 3t. You're going to get y equals 11 over 3 minus 1/3 t. And you're going to get z equals t. These are your parametrics, and we're going to take a look at them a little bit closer. All right, so looking at these parametrics, these are my answers. X equals 7 over 3 minus 2 over 3t. Y equals 11 over 3 minus 1 over 3t. Z equals t. As parametrics, we can change this to vector equation. The point will be 7 over 3, comma 11 over 3, 0, plus -2 over 3, -1/3, 1t. So, that's an answer. It's not a very pretty answer. I would rather have integers here rather than fractions. So what I'm going to do is I can change this to integer values pretty quickly. This is a direction vector, and the magnitude of the direction vector does not matter. Okay, it's just its direction. So the direction vector I can easily multiply by -3, and what that'll give me is 2, 3, nope, sorry, 1, and 3, negative. Better check that. So that'll be 2, that'll be 1, that'll be -3. That's my new direction vector. I haven't worked with the point yet. And there you go. So that's a very good answer. These are both the same answer. This one's a little bit nicer because my direction vector is easier to work with. It would be nice if I could do something with this, but I can't just multiply this through by 3. When you're talking about a point in 3 space, you're talking about this point here, 7, 3, 11, 3, 0, with its position vector to that point. If you were to multiply that by 3, you'd be moving to a new point that's 3 times as far away from the origin. That's not what we want to do here. So we have to find a way of changing this if possible. What I notice is that if I add multiples of this direction vector, notice the denominators are the same. That's the tip-off here. I don't want to add this direction vector. I want to add this one. So I notice that if I start at 7 over 3, and if I add 2 t's, which means it'll be adding 2 over 3, 2 over 3. That's going to give me something interesting. I'll come back to that for a minute. But if I do that, I'm also taking the 11 over 3, and I'm adding 2 direction vectors of this one. So it's negative 1 over 3, negative 1 over 3. I'll come back to that. And I notice that if I do that, I'm also taking this value of 0, and I'm adding 2 values of that one. So it'll be plus 1, plus 1. What we end up with is 7 over 3, subtract 2 over 3, subtract 2 over 3, which I believe is 3 over 3, which is 1. 11 over 3, subtract 1 over 3 is 10 over 3, subtract 1 over 3 is 9 over 3, which is 3. 0 plus 1 is 2, meaning if we move 2 direction vectors down the line from this point, we come to a new point, which is 1, 3, 2, and I can use the nice form of the direction vector, 2, 1, negative 3, and I have a very nice integer answer only for the line of intersection between the 2 planes. Okay, ladies and gentlemen, that's it. That's all she wrote. We will talk to you later. Remember to use the class chat for help, and we will see you tomorrow. Bye-bye.